Okay, resonance structures. How do you stabilize a cation? Move electrons towards it. Pi bond windshield wipers over. You get this resonance structure with a plus on the carbon there. From there, the lone pair can move in, and we can get this resonance structure here. The charge now on nitrogen. That would be it. You do not want to windshield wiper that pi bond over because then you'd leave the oxygen without an octet. You don't want to do that. Two resonance structures that involve delocalization of the cation. Cation's been delocalized and that are more favorable than the one shown. Why are they more favorable? I could have also said just as good. I didn't want you to show anything worse than that, like showing oxygen without an octet. Which one of these is major up there, of the three? Shayna, which one's major of those three? Kendall? The one with the most bonds? Yes. Over here, a major resonance structure. Okay, which amine is most electron rich? The one on the far end? How do we do? Questions? Why is that one the most electron rich? Kayla? Because the lone pair, oh, did you read? Yeah. The lone pair is not conjugated. Okay, there's no p orbital. The lone pair is sitting right there on the nitrogen. And all the others, the lone pair is delocalized into the ring. That's an sp3 lone pair. All the other lone pairs on nitrogen are in p orbitals, being delocalized. Of the other three, we could ask which is most basic of the other three. Which is most electron rich of the other three? Yeah, the one in the middle. Okay. Hopefully you've done resonance structures on the resonance sheet. Yesterday when we tried to look at them, it didn't seem like you had done those. You doing resonance structures on the resonance sheet? If you have any questions about those, please ask. Okay. Expected product, one on the far right, how do we do? Questions? Sophia? Why is that one the most?
I think because it is on the tertiary carbon, the cation would be.
The what's on the tertiary?
The carbon cation would be on the tertiary.
Yeah, but this carbocation is also tertiary. I mean, that's a carbon, carbon, carbon. Well, you do it like this. I went with the far right alkene. That gives cation here, resonance here. That's tertiary. This is tertiary with resonance because that's a benzylic cation. That's the benzene ring. We can do resonance. If we have a cation here, we can do resonance. If you do reaction here, you're going to give cation secondary, resonance primary. Secondary primary is not as good as tertiary and tertiary with resonance. Once we get these, heat, what product is formed with heat? Most stable. Which is most stable? Well, if chlorine adds up there, you get this. If chlorine adds over there, you get this. Which one's most stable of the 1 and 4? 4. Why, Zach?
Because the alkenes are substituted.
How many substituents on this alkene?
3.
How many substituents on this alkene?
3.
3. So why is that one more stable? It's not because it has more substituents.
It's part of the conjugated system.
It's conjugated. The pi bond is conjugated with the ring. Here the pi bond is not conjugated with the ring. Conjugation is better, right? First thing we looked at with resonance was conjugation. Conjugation is better. How we do on that one? Questions about that one? What's up with that one? Questions about that one?
Why did you start on the alkene on the right?
I just happened to. I saw that it was tertiary with resonance. And then I sort of looked at the other one. Can you envision the other one is going to be secondary and primary?
Well, then you-
Why couldn't you get
tertiary.
tertiary there?
Do you rack this one?
Mm-hmm.
Well, where are you going to put cation, left or right? Okay, if you put it on the left, it'll be resonance stabilized by the ring, but it won't be resonance stabilized by the other pi bond. You're going to put cation in the middle of your diene. This is going to give here secondary, and when we do resonance, what type of cation we're going to make?
Primary.
Primary. Do I have to draw it? You need to be able to envision that. I'll move it over here, pi bond here, that's going to be a primary cation. So it would be secondary and primary. Which is better? A cation that has characteristics secondary primary, or one that has characteristics tertiary and tertiary with resonance? It's another cation over there. So you're not going to do this way. You're going to go this way. And then chlorine can add to either position. If it adds there, it's 1, 2. If it adds here, it's 1, 4. But which product are going to get the heat? Most stable. You can either get this product or that product. Of the two, which is most stable? Well, that's certain, because the double bond is, not because it's more substituted, they're both tri-substituted. But one is conjugated with the benzene. That looked like you don't believe me. Question?
Yeah, why wouldn't you want chlorine to be closer to the benzene ring?
For what reason? What have we talked about where we want chlorine closer to a benzene ring? Digestibility of products with these, or substituted. But you can also judge by conjugation, right? Which is more stable, the conjugated pi system or non-conjugated, or two separate pi systems? Look over here. Remember, look this, which is more stable? This one or that one? This one. Got a lower heat of hydrogenation. Pi bonds conjugated. You'd rather have more pi bonds conjugated than not. Right? Okay. Is there any argument for why it should be another product here? Okay. Well, below it deals all the reaction. I have this diene with an oxygen bridge. Alkene, 4 plus 2 is 6. Just put the oxygen bridge. These groups are trans, so now these two groups over here are trans when you got your tetrahedral carbon. How we doing? Brennan? Below acylium ion cleavage, make cation next to lone pair. But I ask you for the major resonance structure. Major resonance structure would be the one with more bonds. Make the extra bond plus on oxygen. How we doing? Okay, those would be posted upstairs, 3rd floor. Any last questions about the quiz?
For the lectures, how would you know to make a triple bond? Like, how would
How would you know to make a triple bond?
like, why is it better to have the plus on the oxygen?
More bonds. right? We've seen resonance structures, first thing we're gonna look at is more bonds. Golden rule number 4 of resonance. Look at golden rule number 4. As long as the oxygen or nitrogen has an octet, it can take on a positive. You got golden rules of resonance? Golden rule number 4. Okay. Any last questions about the material before substitution? We'll get back to substitution. Anything about resonance? Got your composition notebook with all your questions written down? Questions?
So, in this general substitution reaction, you would,
Substitution reaction. Okay, before we talk about substitution, any last reactions, any last questions about conjugation, resonance, mass spec? Question, you Tom?
For the last question on the quiz, would the reflectivity be also one of the minor resonance?
Reflectivity can always happen with ketones as long as the ketone has what? There's a requirement. Gamma hydrogen. That means a hydrogen on not the alpha carbon, not the beta, but the third carbon away. Yeah. Those can undergo McLafferty rearrangement. Yeah. And that one did have a, yeah, that one could go undergo McLafferty. Kayla?
Okay, so for resonance structures with like acid or base, for most acidic, it's the one where you can really less charge the most.
Not necessarily, because phenol is not more acidic than carboxylic acid. In phenol, you can delocalize the minus more, but you're delocalizing onto carbons. And so it's really not that good.
Right.
Carboxylic acid, you can only delocalize the minus onto the other atom, but that other atom is oxygen, so it's so much better. So that's sort of a different consideration. So it's one thing contradicting the other. If you're putting the charge on all the same type of atoms, like all carbons, then it doesn't matter. Carbon's a carbon. Then you say, well, I'm spreading it over more carbons here than there. But if you start putting it on an oxygen, it's a whole different ballgame. Because oxygen loves minus. Question?
With the 1, 2, and 4 addition, with the cold temperatures, can you assume that you don't have to consider resonance? Whereas with the heat, that's when you would consider resonance?
Yes, that's essentially, yeah, that's a good point. Problem is, you do have to consider resonance to which pi bond are you reacting?
didn't we,
Because you still have to, back over here, you still have to consider resonance, okay, which pi bond am I going to really react? And so I did resonance, where to put it? So I considered resonance, and I said, okay, I'm making a tertiary and whatever. If this had been cold, I still would have did this consideration. But if it had been cold, what would the product have been?
1, 2, kinetic?
Actually, would have been the same product. Because cold would have been 1, 2, right? 1, 2. Cold would have been the same exact product. But see, I still would have had to consider resonance to see which cation, because, you see?
didn't we,
But you're on a little bit something there. You don't... Okay.
but when we determined which, on the other one that we did not go with, I feel like we chose the one that wasn't in the ring to be the more stable way to build the alkene. Whenever you decided to put that on the secondary group instead of tertiary group, because the carbocation was more stabilized by that other double bond than it was by the phenyl ring, or the benzene ring.
Okay, I didn't give you the whole, let's go back to it, okay? Let's do the cation there. Because you're right. Typically, you want to put the cation in the middle. If that wasn't there, you put the cation in the middle because it can be resonance. But you're saying since it's there, you want to put it here, and so you react it this way. And we got, let's do it. Let's do it that way and still compare it over there. I'm going to draw out the ring. So new H here and plus here. Right? And then we can draw resonance with ring. And there's 3 resonance structures you can draw. I'm not going to draw them. Okay? Can you do any resonance with that over there? No, because it's pure. So we have a original cation and then resonance with the ring. Well, what do you have if you go this way? You have original cation, then you have resonance with the pi bond. How many total resonance structures over here? If you count that one, there's 1, 2, and then resonance with the ring for a total of 5. Over here you have 1, 3 for a total of 4. And everything is on carbon. So would you rather have 5 resonance structures or 4? 5, more delocalized. So you're right, I didn't point out that, but still that's the better cation. And that's the one that's going to form. In the end, just about always, I don't know what the exception is. Your dienes, you're going to put the plus on one of the middle carbons and take advantage of the resonance from the other pi bond. Now, I suppose I could give you one where it went the other way. For example, if you had other groups on here, like, and then you can draw, but still it wouldn't matter because whatever you can do on this side, you end up doing it over here with that guy. But over here, you got the additional resonance structure from the other pi bonds. There's no way for this way to be good, better. I see no scenario where that way is better. Okay. Other questions about the material before substitution? When's the test?
Wednesday.
Wednesday? Okay. Well, if there's no other questions, we'll plow ahead. This is a handout for our next handout after substitution. This is a handout on elimination reactions. Okay. And these mechanisms over here, we're going to cover this today. Yesterday, the leaving group was what type of atom? What left in our mechanism yesterday? A bromine? Bromine left the tetrahedrocarbon. In most of these mechanisms, what leaves the tetrahedrocarbon? Oxygen. See, oxygen can also be a leaving group. And this is where we're replacing oxygen with bromine. So bromine is the nucleophile. And we will cover that today. Many other things can be leaving groups. Okay, we introduced SN1, SN2, along with reaction coordinate diagrams, defined what the 1 and 2 mean, kinetics with the rate equation, Then we look at stereochemistry, and this ultimately was an SN2. We knew that because SN2 does inversion with backside attack. Because when you kick off a leaving group from a tetrahedrocarbon, you do it backside. On the other hand, if you attack a carbocation, you attack from either side. And so you get front or back in your outcome. So this tells us it's SN2. We answered this. We showed the inversion, how it goes through. The transition state is what type of hybridization mode? It's sp2. It goes trigonoplanar. It goes tetrahedral. The intermediate, or the transition state, is sort of planar, with almost like a p orbital. And it's almost like trigonal bipyramidal. But if you just call that a p orbital. But importantly, what type of bond angles have to be achieved in the transition state?
120.
120. 120 between all your groups on the carbon. Well, the three, not the two that are the one incoming and the one outgoing, but the remaining three. When you started, what was the bond angles between the groups on the carbon? 109.5, because we're dealing with a tetrahedron. Okay? So knowing that it has to go to 120, you can evaluate some reactions and say, hey, those angles are not going to go to 120. I know that for some other reason, and so this is going to be a difficult reaction. There's a couple of questions in the workbook that allude to that. Okay. Now moving ahead, what we're going to do is we're going to focus on SN2. That is the concerted backside attack mechanism. We're going to look at different things, different features of it. First thing we're going to look at is various electrophiles. The electrophile is the thing that has a leaving group. Typically your main substrate, carbon with the leaving group. What do we call electrophile? These are all the electrophiles because there's a partial plus right there due to the dipole. And partial plus likes electrons. And something that likes electrons, we call it an electrophile. Like wine, we call it a winophile. Okay, let's look at how the reactivity of these things can change. First thing is that the effect of a p orbital being immediately adjacent to the reaction site. This is the reaction site. If we're going to kick off that chlorine and put something else on that carbon, carbon's your reaction site. Is there a p orbital immediately adjacent to that carbon? Yes. Okay. What about over here? Is there a p orbital immediately adjacent? Yes. How about over here? Yes. How about here? Yes. There's actually two adjacent there. Only one is really going to be influential. All of these are very reactive in SN2. They're much more reactive than just say this guy. Is there a p orbital adjacent atom here? No. Why does having a p orbital adjacent make it much more reactive? Well, here's the obvious answer. It lowers the transition state energy, right? Then the question is, well, how does it lower the transition state energy? Well, it stabilizes the transition state. Well, then you ask, well, how does it stabilize the transition state? Well, we had it up there yesterday at the end. During the transition state, what type of orbital sort of appears, it looks like, between the incoming and the outgoing? P orbital. Okay, now if that takes on a p orbital in the transition state, and there's a p orbital next door, what can the two p orbitals do? They can sort of conjugate. And with that conjugation, that stabilizes the transition state. Okay? I'll try to draw it back up there real quick. Didn't we have something that looked like this? And the OH was coming in, the Br was coming out. And then at the end I drew how this is like a p orbital. takes on. Okay? Now, if next door there's a p orbital, how can that stabilize this? It can overlap. And orbital overlap is typically always a good thing, unless it's not. In Nordic 2, we'll see where it's none. Sometimes that's called when you deal with aromatic compounds. But here, the overlap stabilizes the transition state, makes it easier to do. If there's no p orbital next door, you don't get that overlap, you don't get the stabilization. All these are very reactive in SN2. Okay? Most of these are up here are also quite toxic. Because they're so reactive, if you get them in your body, your proteins will start reacting and doing SN2. Your proteins have like nitrogens with lone pairs. Those nitrogens will attack and kick off the chlorine. Then you'll end up alkylating your proteins or your DNA. This guy down here is not as toxic. This is going to be a tougher reaction. In fact, if you ever watch baseball and a player like fouls a baseball off their ankle and the trainer comes out, what does the trainer do? They spray something on the ankle or something. Actually, to numb it. What do they spray on? What? I can't. Lidocaine? No. I mean, it could. Lidocaine is an anesthetic. No, they spray that, ethyl chloride. I used to, back when I watched baseball. That's in papers. Why do they do that? Because that's a gas, but it's compressed. And when they spray it, it immediately evaporates. But as it evaporates, it takes heat to evaporate. Where does the heat come from? The surroundings. And if you remove heat from the surroundings, what happens to the surroundings?
Cools in.
It turns cold. It makes it cold and numb. But, I mean, this is potentially SN2. You could have a nucleophile attack here. It's hard. It's not an easy reaction. There's no p orbital next door. So it's not that toxic. They would never come out and spray one of these. These things are like tear gas. They get in your eyes and your proteins start reacting, okay? These are much more reactive. By the way, back in the World Series, the Braves were in the World Series way back when, somewhere, I don't remember when. Anybody remember Tim McCarver? He was the announcer. Okay. He said, the trainer's coming out and spraying some ethyl chloride on him. Called it ethyl chloride. They didn't know it. Alpha chloride. Instead of ethyl chloride. Right there in the World Series. Okay. So p orbital. Another thing, effective carbon substitution at the site of attack. Not next door, but at the site of attack. If you look at this series of alkyl bromides, carbon with a bromine, this one's most reactive. Of course, this is a CBr with just H's on the carbon. This guy over here, instead of 3 H's, has 3 methyls. We call that, this is a primary halide, because the bromine's on a primary carbon. Secondary, it's a tertiary halide. That's sort of just known as the parent. It's not even primary. Most reactive, least reactive. This is most reactive because the nucleophile can just get right back in there and kick off the bromine. The H's are so small. But over here, remember these are carbons with H's on them. If you draw in all those H's, the nucleophile is like, how do I get in there? Okay? It's blocked. This is called sterics, or steric congestion. Okay? Hopefully it just intuitively makes sense. All right?
So if, for the first part, if it stabilizes the entry into the transition state, wouldn't it destabilize the exit from the transition state?
You mean the P orbital?
Yes.
No, the P orbital stabilizes the whole transition state. This is just blocking it with groups, okay? Aaron, pretend you got a leaving group sticking up your back, bromine or iodine, okay? Here's a nucleophile. Just hold your hands down. I just come in, boom, kick off the leaving group, okay? Now hold your hands up this way. Pretend you got two methyls there. Hold them up there. Now he's got two methyls on that carbon, and I come in, I'm like, I can't get there. Move your arms. Now, okay? Those methyls block. All right? Everybody get the picture? Here's the take-home. Never do SN2 with a tertiary halide. It's too sterically congested. Which one's most reactive? The one that's least sterically congested. Something like this. In fact, that guy right there is quite toxic. So the proteins in your body have like amino groups. And these can just, boom, do SN2, kick off that bromine. Actually, methyl bromide is used to fumigate and kill like rodents and insects. It's not used in like small homes. They use something safer. If they've got like a big warehouse, like a 10-story warehouse in New York City that's like real old, it's like full of roaches and rats, they'll come in and they'll just spray methyl bromide everywhere and close it up. And then all the proteins in the rodents will just be attacked and react with methyl bromide. Very toxic. As you get more substitution, it's not as reactive and thus not as toxic too. And if you try to do a reaction with like this one, it's just going to be slower. If you're doing it in the lab, you might have to heat longer. Okay, so this is a couple of things with your electrophile, the thing with the leaving group. By the way, this is your trend for SN2. Faster, slower, never do. The trend is just the opposite with SN1. Because in SN1, what's your intermediate? Carbocation. And what's the best type of carbocation? Tertiary. See, the one on the end is going to form the best cation. So your trend is just the opposite with SN1. That's your best substrate for SN1. All right, now we're focusing on SN2. We'll eventually get to SN1 and see a few things. This is just a table showing the trends that we just talked about. Lithium iodide, well, that's lithium plus I minus. What we're showing here is really one halogen displacing another. I mean, you can do that. SN2, backside attack, kick it off. The rate of these reactions, here's your methyl bromide, the one that reacts very fast. Relative rate of 163. Once you start putting more carbons on the carbon that's attacked, it slows it down. 163 times less reactive. Even less reactive. Tertiary, it's called negligible. Basically, never do SN2 with a tertiary halide. So that's just some actual data. It comes from lab. We can also take a trip to the dentist. You mentioned, you said lidocaine or something? Yeah. Something that's used as an anesthetic for dental work. Not really showing you any structures here. Anybody interested in dental school? Well, you have your anesthetics, lidocaine, etidocaine. The difference in these is the duration of action, how long they last. Some last like 10 minutes. Some you stay numb for like 6 hours. And so you, dentists don't want you to stay numb for 6 hours if they're only doing a 5-minute procedure, right? Well, what is the duration based on? How long the drug survives in the body. The drug is metabolized by chemistry. But sterics, the crowding thing, can slow down the chemistry. Now I'm not showing you the chemistry that takes place here, but the longer acting anesthetics are the ones that are metabolized slower, and they're more sterically crowded around the reaction site. They're more branched, and it slows it down, makes them last longer. If you're interested, you can compare like these two on the wiki. Look them up, they'll show structure. And look how they're more branched. The tinocaine is more branched. It lasts longer. Now, that's an application of the steric hindrance. Okay. So we looked at sort of this guy. Sort of the carbon. Let's look at the leaving group ability. The thing that's leaving. Your halogens are your best leaving groups, with iodine being your best, then bromine and chlorine. And those are much better than fluorine. Typically, F is not a good leaving group. Iodine's best, but it's kind of expensive. Bromine is great, not as expensive, so bromine is usually the best around. Chlorine is cheapest, but it's not as good as bromine. It's a little sluggish and wanting to leave. And then fluorine is just not good. Fluorine's also expensive, but so in the end, bromine typically is kind of your best in terms of cheap and still a great leaving group.
So I think we covered this before, but basically the fluorine would give a greater partial positive on the, but it would have a less stable fluoride ion. Is that the idea?
There is some kind of conflict here. There is some conflict. Which one has more partial positive? Yeah, there's more partial positive there. So you might expect your nucleophile. What's the nucleophile here? We've got to be able to recognize nucleophiles. O minus, K plus. Okay, this is organic chemistry. Let's get rid of the spectator ions. O minus. These electrons come in here, kick off the iodine. Okay? That's how you can get the O bind to the carbon and the iodine get kicked off, and we can show the potassium with the iodine now. All right? That's pretty easy. Iodine is a great leaving group. This is going to be very difficult to impossible. Yes, you have more partial positive there. So how do we explain this? Yes, this may be attracted there more. But what all goes on in the rate determining step? Not only does this have to add, but that bond also has to break. Well, if you look at bond strengths, a CF bond is much stronger than a CI bond. And that plays into it. It's not just the amount of partial positive, but the bond strength is also important because it has to be broken in the rate determining step. Another way that we can look at it to get the right answer is over here. Forget about the K. That's I minus and F minus. We can look over here. Which is more stable over here, I minus or F minus?
I minus.
Sarah? I minus or F minus? Somebody said it. I minus. Why, Amanda?
Well, I would just say because fluorine is more like a negative.
Well, that's a counter argument. I mean, fluorine going more like the negative sounds like fluorine likes minus more. And that would make you say that fluorine is more stable. Actually, it's I minus is more stable. Why, Utah?
Iodine is bigger.
Because it's bigger. Remember we talked about the size? I minus is more stable. So that's another reason that I is your better leaving group, because you get the most stable thing. Most stable thing is produced. Also, it's a weaker bond you have to break. Okay? Very often you have conflicting points in organic chemistry. Ultimately, we know that this is the easier reaction. Go to lab and it's easier, so we have to explain it. Okay, so those are your halogens, most common leaving groups. Oxygen. Can oxygen be a leaving group? Yes. But you have to activate it somehow. It's not going to leave on its own in a rate determining step. You have to activate it. And you activate oxygen by protonating it. Now, this is an additional step in the mechanism, sort of an activation step. Take a look at this. You take this alcohol and try to react it with the same nucleophile, and we're going to maybe try to get this to come in, kick off the OH, and now have O-methyl binding to the carbon instead of OH kicked up. That reaction doesn't take place. It does not happen. That is, OH minus will not act as a leaving group in a slow rate determining step. Why do I point out slow rate determining step? Think about the two mechanisms, SN1 and SN2. Which step does a leaving group leave in SN2? Well, it's only one step in the substitution, is only one step. It leaves in the only step. That step is rate determining, so the leaving group leaves in the rate determining step. What about SN1? Does the leaving group leave in the rate determining step? Yeah. What's the rate determining step of SN1? Ionization of the leaving group leaving. Both of our mechanisms, the leaving group leaves in the rate determining step. So you may say, why did I say this? Because in organic 2, we see leaving groups leave in the fast step. And if the leaving group leaves in the fast step, you don't have these restrictions we're talking about right now. But SN1 or SN2, this applies. Okay, if you want to get this substitution reaction to take place, you do it like this. You include some acid, protons. And then you have your nucleophile. And the first step here is, this is actually catalyst. Okay? And the first step is you protonate your alcohol. You add a proton to it. It's just an acid-base reaction. It's just the OH acting as a base. Protonated. Now we have a good leaving group. Now we have a positive oxygen. Now we can get some nucleophile. I'm using methanol. Now a nucleophile will come in and do our backside attack, kick off the leaving group. And what do we get? We don't get final products yet. We get, what does that arrow movement give? I now have bonded to this carbon what? Oh, the methanol is now bonded. But that oxygen has a methyl and an H. One lone pair remaining. We just made that bond, and that's a positive charge. And what was the leaving group? What got kicked off? Not hydroxide, but water. See, water is the leaving group here. Not hydroxide. Hydroxide will not act as leaving group. But H2O will. alternately, we can also look here. A neutral oxygen will not leave, but a positive will. Because it wants to become neutral. It's okay.
Since it has a greater number of sp3 stabilizing it, wouldn't that hydrogen protonate to methanol before it would protonate to propanol in this reaction?
Yes, protonate. No, these are equally basic. They're equally basic. You can protonate that. Yeah. You can protonate both of them. But protonating that's not going to get you the products. I'm showing a mechanism for forming the products.
I was saying, what can you do in physical reality where you would protonate one versus the other? Is it just volumes of them? Just have them.
This proton is protonating both of them. Not at the same time though. It only protonates, it's an acid-base reaction. How do you judge an acid-base reaction? pKa's. pK of this is 16. pK of this, it's like hydronium. What's pK of hydronium? Like -5. Which side's favored, 16 or -5? 16. Okay? We're not protonating much here. Okay? The equilibrium lies like that. I mean, that is not considered a base, but it can act as a base. We're only protonating a very minor amount, but that minor amount is the reacting species that reacts. We get this. How do we get final product? We got to get rid of the H. Well, what can take it? There's got to be an a minus here. What do you want the minus to be? How about HSO4 minus? And if that's it, that means we started with H2SO4 as the catalyst. Then this can take the H, leave electrons behind, and that gives final product, and you reform your acid, which is catalyst. How do you make OH a better leaving group? Protonate. Note down here, we used methanol as a nucleophile, the neutral version. We did not use methoxide. H plus and MEO minus are not compatible. You cannot have these two together. Okay? So using methoxide, we use the neutral methanol. That is compatible with H plus. I mean, this is the same thing as saying, can you do a reaction where you have both of these in this available? No, they're not compatible. But you can use water and get the same outcome. That's what I say here. No reaction. No reaction. Here's another example of the reaction. If you take an alcohol with like HI or HBr, you can get the alkyl halide plus water. Mechanism for this? Obviously the oxygen has left. How do you make oxygen a better leaving group? Protonate it. To protonate it, you need a strong acid. You're not going to protonate it with water. You're not going to protonate it with ethanol. HI is a strong acid, so we got H plus and I minus. The first step here would be to protonate our alcohol. And then what's the next step? There's only one more step to get a final product. Then the nucleophile comes in, kicks off the leaving group, and you get those two products. So this is just kind of activation, and then this is your SN2, concerted, kick off the leaving group.
So the activation isn't part of the transition, right? It happens before the actual concerted step.
Yeah, it's a separate step. First have to protonate it. It's very common for you guys to think that since I'm calling it SN2, you're like, well, I thought SN2 was one step. The substitution part is one step. What we have though added to that is an activation to make the leaving group ready to do the SN2.
So would the SN2 step be the rate determining step in this one, or probably depend on the strength of the acid?
That could be sort of debatable. Yeah, depending on the strength of the acid. Show the product down below. What type of chemistry can you envision happening here? Show a reaction product there. Thinking mechanistically. As we do more and more reactions, how you have to approach things is what could happen here? How could these two react? Anybody want to propose the first step? Just the first step in the mechanism, what would you like to do? Protonate the oxygen? We can certainly do that. You can always protonate a lone pair, okay? Protonate the oxygen. Anybody else propose the first step instead, other than that? Do something else? You, Tom? Lauren? Any other stuff? That's the only thing I know that we can do here. Organic 1, never do anything with a benzene ring. You got the alpha group, that's just plain hydrocarbon, not really much any reactivity. The only thing we can do here is protonate the oxygen. And we can get, come this way. Now have an H there, only one lone pair left, and that's a plus charge. Okay? Now we got to beat our minus around. And nothing else, that's it. Did these react in any way? What you got?
I think the beat around with one of those would be or, and then I guess it would move the OH off like it did on the other ones.
So protonated oxygen can be kicked off? Yeah, that's what we just did two times, right? Yeah. So tell me what you want to do with these electrons.
You're gonna take them to the, what is it? You're gonna take them up here to this bone, and then you're gonna move on.
Which,
Well, yeah, to the long. Well, not necessarily the long. Why is the arrow goes to the left here? I'm not exactly
You
sure.
want
where
these
the arrow
electrons
goes.
to attack those electrons?
Well, no, it's not gonna attack the electrons.
What's it going to attack?
It's gonna attack the
Positive charge.
positive charge.
So you want these electrons to attack that positive charge?
No. Wait. I'm not
Okay.
exactly sure what the arrow is actually going to. I kind of know what to do. It's like, I don't know what the arrow means, but I know what to do.
So,
I know what my final
well,
product
damn.
is.
Well, damn.
Yeah.
Well, damn. What does arrow mean? You
I don't know what the arrow is, but I know
Right there.
what to do.
The corner of the,
You gotta know what the arrows mean. That's what mechanisms are. Show all electron movement with arrows. You want these electrons to do what?
Is it like bombarding?
Backside attack, penalty.
Robert?
You're gonna have an arrow going from the bond on between the benzene ring and the oxygen. Those electrons on the bond are gonna move on to oxygen, and then
You want this to point here?
no, they're gonna not that. There's a second arrow that gets thrown from.
So you want these to go where?
Okay, those electrons are gonna bond to the phenyl carbon.
Here.
Yes,
And do what?
knock off the.
You
protein
want these electrons
to
to
move on to the oxygen.
do this?
Yes.
Okay.
Can't you knock off the penalty?
What would this give? What outcome does this give? We'll have to come back and look at this. What does this mean? This is making bond to that carbon. That's what that means. There we go. It's now bonding that carbon. Well, that carbon can only make 4 bonds, so something has to get kicked off. And we're saying the protonate oxygen is going to get kicked off. We call that a leaving group. And if it gets kicked off, we have an oxygen now with that and that. 1 lone pair there. But what does this mean? That's moving on to the oxygen as a second lone pair. That's a good stable molecule there. You going to do that? Well, that's what those arrows mean. The question is that what's going to happen? Well, at this point, I'd refer you back to the title of the handout. The title of the handout is Nucleophilic Substitution at what type of carbon? Tetrahedral. Did we do a substitution? We substituted to this carbon. Because we had an O and now we are. Is that a tetrahedral carbon? Is that tetrahedral? It's not. That's not tetrahedral. No. You don't do substitution at a tetrahedral carbon. Not SN2. I'm sorry, you don't do substitution at a triple planar carbon. Okay, somebody have an alternative. We're not going to attack there. Can we kick the oxygen off of some other carbon? Byron, can we kick the oxygen off of another carbon? Which carbon? That one. That's the one we're going to kick it off of, because that's the tetrahedral carbon. The electrons attack here and kick that off. What does that give? Well, that gives the final products, and the final products, let me take us back to the, where are we at? What does that arrow movement give? Here, we're not doing this here. Bromine making a bond there, so we got 2 carbons. Now bromine's bonded there. And then what was the leaving group? What got kicked off? Oxygen with an H, and it has that. There's your product. We don't do substitution here, we do substitution here. What's the leaving group? Not water, not HOH, but HO-phenyl. But what's generally here? What was the leaving group? A positive oxygen. Positive oxygen gives you a leaving group.
So if that oxygen is positive, a partial positive without is it just not enough without the protonation? Right, that oxygen should have a partial positive.
It does have partial positive for resonance, but it's not enough. Needs to be protonated. Let's take a 3-minute break.
The first mechanism, I'm sorry, why can't you do that?
How come you can't do what?
Why can't what, we did first before the second error, why can't we do that?
Okay, why don't you?
The first mechanism, the error, carbon, why can't we do that?
Other than just saying we can't. Well, first off, there's a couple of reasons. If electrons come in, something has to break away. The weaker bond is going to break. Which is weaker, sigma bond to O or pi bond to carbon? Yeah, that could possibly do that. But then we're making minus in the ring. You're right to question that. There are reasons why that doesn't happen. For us, basically, I've just stated, you don't do SN2 on a trigonal planar carbon. You only do SN1 and SN2 on a tetrahedral carbon. Okay? In organic 2, we will do substitutions on a sp2 carbon, but it won't be SN1 or SN2. It'll be a different mechanism.
Dr. Stevens, so it was like, you can look at this real quick. So it was like this, like there. Would you rather do someone, and that's something like, would it be this attention to each other than this one? Because this is closer, and so that could be like a localized charge. So would that be a better?
Well, you messed up there. You said you localized charge.
Would pennant have resonance?
Resonance charges. No, you do resonance with cation.
Yeah, but not really.
No, SN2 doesn't involve cation, right?
Okay. That's just like a partial charge.
Yeah, you don't do resonance with partial charge.
Okay, just,
You only do resonance with full charge. But it would be the one on the left there. Because if you go back, SN2 transition state is stabilized by what next door?
The first mechanism,
The orbital and the
so that would be.
there would be a zero going in the adjacent. That's what makes it that sign. Okay, on these mechanisms back here, you can now see with these OH groups, how do you make OH a better leaving group? Protonated with a strong acid. The HBr is a strong acid. And so now you should be able to do the first 3 mechanisms. But you do have to decide is it SN1 or SN2. And if it's SN1, what's the intermediate that's going to be formed? And carbocations are prone to doing what? Rearranging? So when you do carbocation chemistry, you're prone to doing rearrangements and ring expansions and stuff? we've made it to a point in organic chemistry where you really have to learn this stuff broadly and intuitively. For example, the reaction we just did was cleavage of an ether with HBr to get an alcohol. So what? Please don't memorize that. You can all look at the product. Did we form an alcohol as one of the products? It's called phenol, but it's alcohol. Yeah. Please don't memorize. Learn mechanistically, intuition. Okay, what's going to happen here? Make your decision. If you learn like that right now, you get to organic 2, it'll be much easier. All you've done is memorize outcomes. If you're not taking organic 2, you're going to get bogged down and it's quite difficult. It's sort of like reading. You learn how to read. If you don't memorize every word, actually, I think you do memorize every word. It's like math. Okay, as I said that before. You don't memorize every answer. I mean, I have. I mean, I know 75 times 75 is 5,625. But I wouldn't recommend doing it. Okay, it takes too much time and you get confused. All right? You have a method of approaching things. Okay. Okay, what's another way to make oxygen a good leaving group? The other way is not as common, but it's still highly important. And of course, it's a textbook reaction we need to be familiar with. Where are we at here? The other way is to actually totally convert it to a new functional group. Convert the OH to a tosylate. Tosylate is the one that we see at this level, introductory organic. There's variations of tosylate called mesylate or triphlate. This is a tosylate. So instead of having OH, we're going to make it O with SO2 and a group. If the group is, that's called benzene with a methyl. That's called toluene. You can buy it at Lowe's in the paint section. Toluene hooked to the sulfonyl. It's toluene sulfonyl. O-toluene sulfonyl. The toluene sulfonyl is sort of abbreviated as TOS. That's what that stands for. I do TOS. It's actually not correct. Usually 90% of the time you see it OTS. I like to put the O in there so you remember it's awesome. Okay? So that's what you'll probably see in the textbook. Now this group out here beyond the SO2 can vary. If it's a methyl, it's called mesylate. If it's a CF3, a trifluoromethyl, it's called triphlate. Now triphlate is actually the best one, but you don't see it at this level. Now let's look at these. All of these are good leaving groups. Okay, probably says that up right there. These will serve as leaving groups without the need for an acid catalyst. You don't need to protonate them. That is, a nucleophile will just come in here and kick that oxygen off. Now that's a big leaving group, there's a lot to it. But when it gets kicked off, what do you end up with? You end up with, now your nucleophile bonded to your tetrahedral carbon, plus your leaving group. Your leaving group was what? Oxygen, SO2. Now, an aromatic ring is often just abbreviated sort of with a phi symbol. I'm just going to abbreviate it. All right?
Thank you.
But you need to know what a tosylate is. What's the charge of this oxygen now? How many lone pairs on it? Now 3. And thus what's the charge? Yes. Okay. Up here, if we kick that off, it would be hydroxide leaving. Hydroxide, as we said earlier, will not be a leaving group in the rate determining step. That minus will not. This one will. That implies that that's more stable than this. Why is this more stable than hydroxide? Starts with a res. Resonance. The leaving group is highly resonance stabilized, thus it will actually leave. It's okay. I don't mind leaving. Kick me off. Because we can do resonance, electrons here, and hopefully you have a little bit of room there. What does that resonance structure look like? We now have double bond to S. This is single bond with a minus. And then your toluene group.
How do we do that?
So your tosylate, this is called a tosylate, is a resonance stabilized anion that will serve as a leaving group without the need for acid. These others will also. I mean, you can kick this and kick off the mesylate or kick off that.
So how do you convert the OH to the tosylate in the first one?
We're going to look at that briefly. That's down below. Let's go ahead and do that, then I'll come back and I'll mention these two.
Professor, would possibly not be both for, as in the start making during the substitution?
It is a little bit, but it's away from the reaction site. I mean, the reaction site is here. It is a little bulkier, but the reaction site is still classified as what type of carbon? It's tetrahedral, but in terms of primary, secondary, tertiary. Still primary carbon. So it's not really, whenever that substitution, mainly you want to start here. It can be close by. Yes, it's bigger than like the bromine, but it works. Okay. Now we got to, how do you make a tosylate? Well, you use tosyl chloride and like a base like pyridine. Now, I'm not going to do this mechanism. Could, but we'll do it in organic tubes. But let's show what tosyl chloride is. Well, tosyl is, it's really toluene sulfonyl. So it's CH3 and then the sulfonyl. O-TOS would be an oxygen here. This is Cl-TOS. So here we have a chlorine. And that's known as tosyl chloride. If you react your alcohol with tosyl chloride, what needs to take place to give this? The chlorine needs to be replaced by what? The oxygen. I'm not going to do full mechanism, let's just look at it. And what would be produced here, don't worry about pyridine, what would be produced when we make that? What would you imagine being produced? What other product? HCl. All right? Again, you could give that a try. It's a substitution. The problem is that sulfur is not tetrahedral. It's got a pi bond to it, so it's a little bit different mechanism. It's a substitution, okay? It's a substitution mechanism. It produces HCl. We include pyridine to react with the HCl. Pyridine is a base. Again, I'm not giving you full, complete mechanism, just some information. Importantly, whenever this oxygen reacts with the sulfur and kicks off the chlorine somehow, do we get any change in stereochemistry at the carbon? No. Nothing happens there whenever we bond the oxygen to the sulfur. Why would it? We're doing oxygen-sulfur bonding. Nothing happens at that carbon. Now, if we bring in a nucleophile and we replace the leaving group by an SN2, well, how does that take place? Well, the nucleophile then comes in. Now we're doing carbon chemistry and kick that off. Do we expect a change now? Yes, the leaving group is forward, so how does the nucleophile come in? From the back. So there's when you get your inversion. Not here, because nothing happens at the carbon.
What's the benefit of doing this versus an acid chemist? Do it different.
First off, it's another way to skin a cat. Okay? Maybe your substrate is acid sensitive and it degrades under acid for some other reason. You don't want to have to do an acid catalyzed reaction. Okay? So there are potential reasons. Let's look back at the very first page of this handout where we're making Allegro. What are they doing here and going from 31 to 32? They're replacing right here. What is an OMS? It's not a tosylate, but it's a mesylate. It's the methyl instead of toluene. You're not going to see that in your textbook probably, but it's very commonly used. It's the same idea. So they got a potential leaving group on a tetrahedral carbon. They throw in this molecule. You got lone pairs there and there. Which lone pair is going to be more reactive? This is the same consideration when we talk about bases. Which is a better base, the nitrogen or the oxygen? Nitrogen. Oxygen holds its lone pairs tight. Oxygen is a good parent. Nitrogen lets the lone pairs get out there and react with protons, or get out there and do backside attack. So these electrons do backside attack, and attack there, kick off the mesylate. Now the nitrogen's bonded there. Well, before anything, there's an H there. But the nitrogen is now positive. You've got to get rid of that H afterwards. You have to include a base to take the H. That's why they include potassium carbonate. Take that H away. But this is an SN2 of a mesylate by an amine. We're fixing to look at different nucleophiles and we'll see amines. There's an example in making Allegra.
What's going on with that triple bond right
Do what?
there? What's going on with that triple bond?
Well, the next step, they hydrate it to make the ketone. Aren't y'all doing that in the lab? Y'all just did that in the lab? Yeah. Y'all used sulfuric acid. You didn't use mercury, though. Yeah. Now, see, they had no H here. Ah, I know why they didn't use acid. Why not just protonate this and then bring in this and get it to attack here?
The triple bond what?
Possibly. There's another reason. Because that's a base. You can't do an acid reaction with a base around. That's like having your cake and eating it too. Alright? So there's reasons why he said that they made the mesylate and then they reacted it with the amine. In the end, it's just a different approach. And it's, okay, let's see where we're at. Here we go. Oh, what are these other two? These other two are sort of variations. Like this guy here. I mean, it's just one carbon shorter, but that side is the same as that side. The difference is it has another O over here. But still, nucleophiles can attack here and kick off there. So the whole thing is a leaving group. These two are actually super common because these two are actually diesters of sulfuric acid. I mean, if you draw sulfuric acid, it looks like this. Here, we just put alkyl groups there and there. But at this point, these carbons have leaving groups. And you can supply an alkyl group to your nucleophile. Same thing here. That's called dimethyl sulfate. That's called diethyl sulfate. These are commonly used to supply alkyl groups to nucleophiles. They're cheap. You can buy gallons of these for a few dollars. These up here typically have to make by methyl chloride. Okay? Similar idea. Only one side is really serves as the reactant species. The other side is part of the leaving group. Terminology. This reacts here. We now put a alkyl group on our nucleophile. That's what we're doing. What do you call it when you put alkyl groups on things? Alkylation. Okay? All right. Have you ever heard of alkylating your DNA? Leads to cancer? Okay? Just terminology. But a lot of times terminology is quite simple, but unless you hear it and really see what's going on, it stays kind of not simple. Okay? These are great alkylating reagents. They supply alkyl groups because the alkyl has a leaving group on it. Okay. Can nitrogen be a leaving group? It can be, but it's even more rare. And this is actually, this reaction is sort of just a very rare curiosity type reaction. But it can be. Herzig-Meyer. I think they sell furniture on Wrightsboro Road, but they also do this reaction here. If you react this with HI, you can get this. What's happening? This is not an alkylation. We have two alkyl groups on nitrogen, and now there's only one. That's not an alkylation. It's a dealkylation. How is this dealkylation happening? If you heat this with HI, you can dealkylate the nitrogen. What's happening here? The iodine is now bonded to one of the methyls, and so is the nitrogen.
The nitrogen take the hydrogen and kick off the methyl,
So you tell me, keep talking. This takes this,
and then the methyl kicks off the methyl.
and we have, hold on, no. That's a plus charge. Now I've got a positive nitrogen. Let me draw these out as CH3s. It really doesn't matter. Now we got a minus. What do you want to do now?
Attack one of the CH3s with iodine.
Attack here and kick off the nitrogen from the tetrahedral carbon? Can we do that?
Seems like
That's what we've been doing. The only difference here is a positive nitrogen is the leaving group instead of a positive oxygen. Okay? This is an example. There you go. That gives methyl iodide and their nitrogen. Okay? Hopefully you see this is just another example. But this is a case where nitrogen can be a leaving group.
how would we rotate that lone pair? What's the idea behind that? Is it really, really strong acid?
HI is a very strong acid. It's one of your 7 wonders of the world.
That'll protonate it as for pure.
That lone pair isn't a p orbital, but there's not any heteroatoms here pulling it, so it's slightly basic. Slightly basic. Okay? Can sulfur be a leaving group? I'm thinking probably so. But just like oxygen and nitrogen, usually you have to make it what charge?
Positive.
Positive. Well, that's what your body does. Sulfur is used as a leaving group in your body. It's also used as a nucleophile. Everybody heard of SAM? S-A-M? They sell it at like Whole Foods and stuff. Found it over in the pill section. It's a methylating agent. Sounds toxic to me, but there's a lot of processes in the body that require methylation. For example, converting norepinephrine to epinephrine. Here the nitrogen needs to be methylated. How is this done in the body? You need a methyl with a leaving group. SAM, S-adenosylmethionine. That's the amino acid methionine that's bonded to adenosine. But right there, the sulfur has a positive charge. The nucleophile attacks the carbon, kicks off the sulfur. And that's how you end up with a methyl on your nitrogen. You got to lose an H. Point that out because that's a biochemical type reaction. Positive sulfur being a leaving group. Anybody ever heard of SAM, SAM? Look it up on the wiki. Alright? Alright. We just looked at, we were focusing then on the electrophile, the thing with the leaving group. We talked about various points about it. Now we're going to move to talking about the nucleophile on SN2. First thing, reactivity of different nucleophiles. The first point is anions are more nucleophilic than the neutral counterpart. Okay, this is pretty intuitive. Both of these will get you an OH on a carbon. That one you're going to have to lose an H afterwards. Which one's more nucleophilic? Anion. Because that's a minus, it's going to be more prone to attacking that carbon that has partial positive. Hopefully that makes sense. Over there, NH2 minus is going to be more reactive than neutral ammonia as a nucleophile. Next point we can make. A less electronegative atom has the more nucleophilic lone pair. Well, this is the good parent, bad parent thing, which we've already alluded to several times. Which is more nucleophilic, ammonia or water? They're both neutral, so you can't use that. Which lone pair, just because there's two doesn't mean anything, which lone pair is more prone to getting out there and doing backside attacks? The nitrogen lone pair. Why? Because nitrogen is less electronegative. Nitrogen doesn't hold its lone pair tight. It lets it get out there and react with things. Oxygen, better parent, holds the electrons tighter. Okay? Less electronegative. It's in the same row there. Okay? We're either going to go across or straight down, at least to begin with. Now let's go up and down. This should still work with electronegativity. Which one is more nucleophilic? H2O or H2S? Well, which one is more electronegative, O or S? O. So that means O holds its lone pair tighter. O is a better pair. Sulfur doesn't hold it as tight, lets it get out there and do backside attack. More nucleophilic. And actually your body uses sulfur as a nucleophile a lot. Over here, which is more nucleophilic? These happen to be both anions. I minus or F minus? I minus. Why? Because F is more electronegative. It holds its lone pairs tight. Which is more stable, I minus or F minus? I minus is more stable also. It's kind of conflicting. The more stable minus is a better attacker? That sounds a little bit like a conflict. Yeah, very often you have conflicts. There's kind of a rationale for that. The bigger halogen can start, the bonding can start earlier. Okay? Pretend I'm going to do a backside attack here. Okay? You got a leaving group kick off your back. Okay? If I'm iodine, I'm huge. This is my core. It's like, I'm starting to bond now because my electrons are so far out there. Fluorine, the electrons are, it's only the one shell. And so the electrons, I got to move a lot closer before I start bonding. So that kind of plays into it. That makes iodine a better leaving group. Ultimately, the answer comes from electronegativity. Iodine is less electronegative, it's a better nucleophile.
So we would say that NH2 minus is a stronger base than OH minus from the same reason, right?
Yes, it's a stronger base. Yeah. Very similar until we throw in sterics. Throw in sterics, base and nucleophilic can become different. Let's talk about sterics. A sterically crowded nucleophile is not as reactive. Look at these amines. They all have the same electronegativity. They're all neutral. So how do you explain this one being more reactive as a nucleophile in SN2? Sterics. We have 2 groups here, and now we have 3. Okay? We did this for the electrophile earlier. Remember I did it over here? Aaron, you had a leaving group out your back, and then I was going to attack you, but then I said, hold up 2 arms. Hold up 2 arms. I can't attack because the electrophile has substitution. Well, now we're just turning it around to me. Okay? Pretend you're the same, you're sitting there, leaving group out the back. Am I going to be able to attack just here? What if I start having substitution? I create my own substitution. I can't get to you because my things are in the way. See, these groups are in the way and it won't let that lone pair get to the backside carbon. This tends to be so your sterics can influence both your nucleophile and your electrophile. Triethylamine over here is often used as a non-nucleophilic base. It's basic, but it's not nucleophilic. This substitution can also be adjacent. Previous example, we started substituting on the nitrogen. Here, we're not substituting on the oxygen because you can't. We're substituting next door. And the substitution next door also hurts the reaction. Maybe not as bad, but it can. Because if I got substitution, maybe it's next door, you might say, well, the oxygen is still attacked. Because there's nothing on the oxygen. Yeah, but remember, maybe the molecule is like this. And it can't attack here. It has to rotate or something. And that rotation is going to slow down the attack.
It'll overcome more negativity based off of the donor? Or is that something that makes sense?
I'm not sure of the question.
We're doing that already.
More substitution here is going to slow it down. Let's look at resonance effects. This should also be intuitive. Which is more nucleophilic? This oxygen or this one? This one. Why is this one less nucleophilic? Elena? This one, the lone pair, let's just consider one of them. The lone pair is sitting right on the oxygen. It's like a big lone pair there. And that's a full minus. Is that a full minus? No. What do we see that can be done here? Yeah, this is resonance delocalized. We can see resonance structures here. And we have resonance structure. And the true structure looks like that. So that's a full minus. Is that a full minus? No, it's just a partial minus because it's partly delocalized. The full minus is going to be more nucleophilic, more prone to attacking that partial positive carbon and kicking off the leaving group. Same thing with basicity. Which is more stable? Well, that, because it's delocalized. Thus, H here is more acidic. And hybridization effects. A lot of this correlates with the acid base. I recommend pulling out that handout to look back. Which lone pair is more nucleophilic? They're both nitrogen, they're both neutral. This is a hybridization. What type of orbital is this lone pair in?
SP3.
SP3. How about this one? SP2. Which one's held tighter to the nucleus? SP2, because it's 33% S, held tighter to the nucleus. And so it's not as reactive. It's similar to the good parent, bad parent. That's a better parent. It's holding its kids closer to home. Can I see this? Hopefully these ideas are sort of reviewed from the acid base. Yeah? These same things influence your... okay. Please do this overnight. We'll look at it tomorrow. Rank the following according to nucleophilic strength. Series 1 and then rank Series 2. And then we'll sum it up. We'll sum up the SN2 factors. Then we'll be moving on to SN1 a little bit. And then we'll be moving on to the new handout, elimination. Please also be looking at the mechanisms on the back of the first page.